In today's video, we will do some practice problems on one-dimensional motion. This will cover both calculus-based and non-calculus-based problems. Problem 1 involves obtaining position and velocity from acceleration and therefore integration. The acceleration of a car is given by this 3t, t is time, measured in seconds, and the acceleration is measured in meter per second squared. Now, if the car's velocity at time t equals to 1 is 5 meters per second, calculate the velocity at t equals to 2 seconds. So this is the initial condition for this part A of the problem. So to get the velocity, we integrate the acceleration function as given, a dt, where a is 3t dt, and that is going to give you 3 over 2 t squared plus an integration constant, let's call it v naught. To obtain v naught, we use the information that at t equals to 1, the velocity is 5, so it's positive 5. So if we substitute that information in here, so when t is 1, the value is 5, but we know v1 from this expression is 3 over 2, 1 squared plus v naught. So that means v naught is 5 minus 3 over 2, which is 7 over 2. So that would give you the complete expression for the velocity function as a function of time, and that is 3 over 2 t squared plus 7 over 2. Now, having found this, we can answer the problem, which is calculate its velocity at t equals to 2. So at t equals to 2, the v is 3 over 2, 2 squared plus 7 over 2, which is 9.5 meter per second, positive 9.5 meter per second, and that's the answer for part A. Having found the velocity function, now we can proceed to determine the car's position at t equals to 2, given that at t equals to 1, the position is 6 meters. So the position can be obtained by integrating the velocity function that we have obtained above. So that is 3 over 2 t squared plus 7 over 2 dt. So the integration of 3 over 2 t squared will give you 1 over 2 t cubed, and the integration of 7 over 2 is quite simply 7 over 2t. So together, the answer for this integration is half t cubed plus 7 over 2t plus an integration constant, which we have to determine. Now we know at x, the value of x at t equals to 1 is 6. So from this expression, when we substitute t equals to 1, that becomes 1 over 2, 1 cubed, plus 7 over 2, 1 plus x naught. By solving this, we can determine x naught, which is 2. So the complete function for the position is given by half t cubed plus 7 over 2t plus 2. So position at t equals to 2 seconds is therefore 1 over 2, 2 cubed plus 7 over 2 times 2 plus 2. And that becomes 13 meters. So that is the position of this object at t equals to 2 seconds. Problem 2 involves determining velocity from the position. So that involves differentiation. We are given a particle's position as a function of time, 9 plus 2t cubed. Now first we want to determine the average velocity of the particle during the time interval between t equals to 1 and t equals to 2 seconds. From our previous video, you remember that the average velocity is given by that equation. So now let's compute the position of this particle at these two different times. So x at t equals to 2 is 9 plus 2, 2 cubed. which is 25 meters. Now, the coordinate at t equals to 1 second is 9 plus 2 times 1 cube, and that is 11 meters. So this expression, the numerator is the change in position between two different times, and the denominator is the time interval between the two times concerned. So by substituting the 25 and 11, so x at 2 is 25, x at 1 is 11, divided by 1, and you're going to get 14 meter per second. So that is the average velocity between t equals to 1 and t equals to 2 seconds. So that's part A of the problem. Part B asks you to compute instantaneous velocity at t equals to 1 and 2. Now, instantaneous velocity, namely the velocity at any time t, is given by the derivative of that position function with respect to time. So now we know what the derivative or the position function is. It's given as 9 plus 2t cubed. So to take the derivative, it's quite simple. The derivative of 9, which is a constant, 0. The derivative of 2t cubed is 6t squared. So the total answer is 6t squared in the unit of meter per second. So at t equals to 1 second, the velocity is 6 times 1 squared, which is 6 meter per second. And v at 2 seconds will give you 6 times 2 squared, which is 24 meter per second. You note that these two values are different from the average velocity we calculated in part A, which was 14 meter per second. This is because what we have calculated here are the instantaneous values, whereas in part A we computed the average value for the velocity. Now part C, what is the particle's velocity when the particle is halfway between t equals to 1 and t equals to 2 seconds? So we need to know what particle is at t equals to 1 and t equals to 2 first. At t equals to 1, the particle's position is at 11 meters. So let's say 11 is here. So this is the x-axis. At t equals to 2, the particle is at 25 meters. So let's assume it's here, 25 meters. So how do we get these two numbers? It's by substituting the corresponding values of t in that expression for x. So the entire distance is 14 meters. So halfway should be 7 meters, 7 meters. So this coordinate, the halfway coordinate, is 18 meters. So when the particle gets there, what is the velocity? So first we need to know the time for which that happens. So when x is 18, which is 9 plus 2t cubed, so the t, value of t, will be 9 over 2 power 1 over 3, which is 1.65 seconds. And substituting that into the term for the instantaneous velocity is 6t squared, as we have seen before. And when it's evaluated at 1.65 seconds, it's going to be 6 times 1.65 squared, and that is 16.34 meter per second. Problem 3 is on kinematics. We shall use non-calculus method to solve this. So an object is thrown vertically downward from the top of a building with an initial speed of 15 meters per second. What is the speed after it has fallen for 2 seconds? So the object is thrown downward like that with an initial speed of 15 meters per second. Now we know the acceleration is also pointing downward, and the value is 9.81 meters per second squared. So in this case, the direction of the acceleration and direction of the motion is the same, so the object will speed up. So after it has fallen for 2 seconds, let's say the velocity is v. So after the lapse of 2 seconds, what is v? That's what we want to find. The equation to use that relates all these variables is the first equation of kinematics, which is v equals to u plus at. We know what u is. It's 15. A is 9.81 and t is 2. And the answer is 34.6 meters per second, as it should, because it's accelerating downward. So part B, how far has it fallen? So it is this distance. Let's call it delta y that we want to find. Now we can find delta y by using the second equation of kinematics, which is the distance it travels equals half times the acceleration times the time it takes to travel that distance squared, plus the initial speed times that time. So now we know that the acceleration is 9.81. Time it takes is 2, so that's 2 squared. Initial velocity is 15 meters per second downward, times again 2, which is 49.6 meters. So that is the distance it has fallen. Now part C, calculate the magnitude of the object's velocity after it's fallen 8 meters. So let's say it is there, and what is the V when the distance it has fallen is 8 meters? Now the acceleration is 9.81 meter per second squared, and we know it's downward. So the object is speeding up as it falls downward. So the equation that we use is the third equation of kinematics, which is 2 times acceleration times the distance it has traveled equals the final velocity squared minus the initial velocity squared. So the acceleration is 9.81. The distance it has fallen is 8 meters. V is what we want to find, and U is 15. That's the initial velocity. And we can solve this equation for the final velocity as 19.5 meter per second. So that is the velocity, 19.5 meter per second in a downward direction of the object after it has fallen 8 meters. Problem 4. A train starts from rest at a station accelerating at a rate of 1.8 meter per second squared for 10 seconds. And then it runs at constant speed for another 30 seconds and finally slows down at minus 3 meter per second squared until it stops. What is the total distance traveled? We divided the motion into 3 segments. The first segment is, it starts from rest, so u1 is 0, the initial speed is 0. The acceleration here for this first segment is 1.8 meter per second squared, and it takes 10 seconds to cover that distance. So delta x1 can be determined by the first equation of kinematics, which is half at squared plus u1t. So a is the acceleration of the first phase. We can even call it a1. So a1 is 1.8. So upon substituting these numbers, you will get the distance it travels in the first phase of the motion. So that u1 is 0 and t is 10, and the answer will be 90 meters. So delta x1 is 90 meters. Now what about x2? It runs at a constant speed for 30 seconds. So we need to know what that constant speed is, that v. This v would be the final v for the first phase. So how do we find the final speed for the first phase? By using the first equation of kinematics, like that. So u1 was 0, a1 was 1.8, and t for the first phase was 10, so it was 18 meters per second. So that means this speed is 18 meters per second. So the total distance it travels for 30 seconds at that speed is therefore 540 meters. The third phase is that the acceleration is actually now a deceleration, which is minus 3, let's call it a3. The final speed is 0, it comes to a complete stop, and the initial speed of phase 3 is the final speed of, or the constant speed of the second phase. So we have all this information, all these numbers for the third phase. The initial speed 18, final speed 0, acceleration is minus 3, and what is delta x3? So we use the third equation to get delta x3. So the third equation of kinematics is 2 times acceleration times the distance covered equals the final velocity squared minus the initial velocity squared. Substituting these numbers inside that equation gives you this, and finally we can get what x3, delta x3 is, which is 54 meters. So the sum of these 3 distances gives you 684 meters as the total distance traveled.